Okay, we're going to have a look at this problem. So you should be able to see my screen, and you'll see two sort of columns. The left-hand column is where I just did the problem to practice, and the right-hand column is where I'm going to record my video. I'm going to flip between the two columns to kind of check my answers as I go through the video. All right, so we're given a hyperbolic conservation law, and we're told that the speed of whatever this stuff is given by half rho. We're given an initial condition for rho, which is a step function. So you can, I guess, think of rho as being some density. Maybe it's a fluid density, maybe it's a traffic density. We're given that u equals this thing, half rho, so that's the speed of the individual elements of whatever this stuff is. Let's just make sure I got this right. I just did this problem, so I'm sure it's right. Yep. X. This is rho. Okay. And that's at time 0. What we've got to do is firstly cast our problem in terms of rho entirely. So we know that the flow, the flux or whatever this stuff is, Q is rho times U. So let's do that and then work out what Qx is. So the flow is obviously just a half rho squared, because we've got a rho there and we've got a half and a rho there. Qx by our product function of a function rule, we've got a half, we differentiate rho squared, we get 2, so we've got half times 2 times rho times the derivative of rho with respect to x. And what we end up with is this Invisib-Burger's equation, actually. Like so. Now, it's quasi-linear first-order PDE. It's amenable to characteristics. Let x be a function of time. So we're following these characteristic curves. Then we want the rate of change of density, rho, with respect to time. So that's a total derivative now, because on these characteristics, rho is reduced to a single variable thing. So our chain rule says this, oops, and by comparison to our original PDE, here, don't have to zoom out, that one and that one, I can see that I got this term, got this, got this term, that term, this term. If that term equals this P here, then I've got my P, I've recovered my PDE. So if dx dt equals rho, d rho dt equals 0. And that's quite significant. D rho dt equals 0 implies that the density is constant along these characteristics. So that means that on these characteristics, our initial condition is going to be preserved in some way. So we integrate up, we get rho effectively equals just rho naught equals 1 or 0, x less than or equal to 0, x greater than 0, right? That's our initial condition, right up here. So that's our initial condition. We integrate, we find that rho doesn't change on these characteristics, so it must be equal to the initial condition, and then we're done, right? We've now got information as to how we can actually solve these characteristics, right? The xdt equals rho defines the characteristic. So rho must be equal to rho naught because the rho was constant on those characteristics. And we're now in the glorious position of being able to sketch these characteristics. Not quite, actually. Our glory will come momentarily. We integrate. Now we can sketch them. So remember, a characteristic is a line in xt space or tx space, depending on how you want to think about it. If x or x naught is greater than 0, we're in here. X is greater than 0. We've got a line. We've got x equals x naught. That means x naught's constant, right? It doesn't move from whichever starting value we give it. So we obviously have very different starting values. Each of these x naughts can be different. If x is negative, then we've got a line of gradient 1 but intercept minus x naught. So we're down here, like in here, we're doing this, which is shocking because the characteristics cross. We said that the density is constant on these characteristics, so we must have a shockwave type solution, or the way we reconcile this is a shockwave solution, right? We've got one density here when we live on the red line, and we suddenly jump to a different density when we intersect with the black line. Now, if we examine a characteristic just to the left of the origin, and a characteristic just to the right of the origin, we'll see that these characteristics actually intersect very early on. There's no time delay in the intersection of these characteristics. Remember, it's neighboring characteristics, which really is like these things are separated by an infinitesimal amount that bring on a shockwave. It's the first intersection, which occurs at 0, which is time 0, which means that we have the shockwave to start with through our system. This shockwave isn't born in some way. How we reconcile shockwaves is we imagine that they're a propagating jump. So because our density looks like this, what we are going to imagine is that's our time 0 density, right? This is our slightly later time density. That jump propagates in time. Our challenge is to find the speed at which that jump propagates. Rho x. Black line is t equals 0. Red line is t equals t star greater than 0, right? That's some non-zero later time used as an illustrative example. All right. What we learned about in lectures was the Rankine condition. We have an expression for jump velocity. Essentially, it comes out of our conservation law. We appeal to that to write dx s dt the speed of the shock wave, right? So we're really tracking this XS location, the location of the shock. The speed of this is the jump in the flow. So the flow on the right-hand side of the jump minus the flow on the left-hand side of the jump divided by the density on the right-hand side minus density on the left-hand side, right? And you'll realize that this gives you kind of like a speed, right? Because if you like, Q is rho times U, right? So you do expect this thing intuitively to yield a speed. You can look up the Rankine condition, or you can go back and have a look at our lecture in more detail. Let me just figure out how to spell the dude's name. All right. We know what Q is. We know what rho is. So we can actually work this out. Right at the start, we said Q equals 1/2 rho. Right, that was, oh, oops, maybe it was rho squared. Yeah, it was rho squared because U was a half rho. So rho squared it is. So when we stick in these values, so to the left or to the right, we get 1/2 rho plus squared minus 1/2 rho minus squared, divide by rho plus minus rho minus. Now this is cool, right? Because we can pull out that half, we can factorize the top. They cancel, and we're left with the speed of the shock wave, our dx ds, t, the speed of our shock wave, is just the difference in our densities immediately either side of this jump. We know that jump, right? We're going from rho 0 to rho 1. That's our initial condition, and it must be preserved. We're all constant on these characteristics. So this initial condition must just propagate at some speed, dxst. Dxs dt. Right, so that's the xs is the location of this shock wave. So let's just plug in. On one side it's 0, on the other side it's 1, so that's a half. The initial location of our shock is 0. Now, we know that because that's where the density jumps at time 0, and we know that the time 0 is where our shock originates. It originates there, which is t equals 0. So xs equals a half t. Now that means that if xs is less than or equal to a half t, rho equals 1. So that's everything to the left of the jump. right? To the left of the jump, rho is 1. To the right of the jump, rho is 0, which I've already drawn in. So that's the solution to your problem. And this shock wave propagates with speed half, right? So the black line is T0. The yellow line is T equals 1. T equals 2, and so on. You get the idea. Alrighty, so that's a shockwave solution to this equation.